Hello, welcome to the virtual tour guide to La Silla Observatory of ESO. Very welcome to all of you. My name is Hernan Julio, and I will be your guide in this virtual tour. I'm a journalist specialized in astronomy, and I have with me also Felipe Zurita, who is going to be our producer today. Hello, Felipe. How are you?
Hello, Don Hernan. Hello, everyone, to see us today in a virtual tour guide for ESO. Today is La Silla, right?
La Silla Observatory, yes. So we will. Well, Felipe also has studied astronomy as a physicist, so he can answer many questions. If you have all the questions that you have, we can answer to you. And please use chat in YouTube or Facebook to ask any question, comments, and also say greetings from where you are looking at, watching us from all over the world.
That's right. Leave your comments, questions, whenever you want about the La Silla, the astronomy, or leave your greetings. I am the producer. I'm showing you all the videos and things in this virtual tour. So let's start, Don Hernan.
All right. Well, we want to say, first of all, we want to introduce to you what is ESO. ESO is the European Southern Observatory. Well, ESO is an international organization. Um, can you give me a minute, please, Felipe? Can you continue a minute, please?
Don't worry. And the ISO is an organization, a European organization with 60, 60 countries. Actually, Australia is the lastest, and Brazil is the other last country in, member inside in the ISO. ISO is organization to build, operating, and move the grid telescope for see the southern hemisphere of the world. So the ISO the principal word is bring us the technologies and the facilities to astronomers to see the sky, to see the southern hemisphere. The ISO start in around the 16, the year of 16, um, because we need to see the other half, the south half of the world. So, but that reason uh, come to Chile and put different observatories. Here's the observatories in Chile. We have a few different. That's right, and here is.
Yes. Well, as Felipe told you, we have this ESO, is this international organization who design, build, and maintain telescope in Chile. What you see now in your screen is the map, Chilean map in the center, of course, and this is a skinny and long country. And you can see to your left you have Paranal Observatory, and also to the right, La Silla Observatory. Well, the first observatory of ESO in Chile is La Silla. La Silla has this one of the most important telescope in the world in the 70s and the 80s and the beginning of the 90s, which is the ESO 3.6-meter telescope and the NTT, the New Technology Telescope. We will visit them today. La Silla was inaugurated in 1969 and was the first ESO observatory in Chile. Now, La Silla is located at about 500 kilometers north from Santiago. You can, if you want to visit us, you can fly to Santiago, and from Santiago take a plane to La Serena or drive to La Serena, and 1 hour and a half driving to the north of La Serena, in the Coquimbo region, you will reach La Silla. We have open doors. We have open doors every Saturday at 10 o'clock in the morning and 2 p.m. in the afternoon. That means that we have visitors. You can visit us every Saturday in the morning or in the afternoon. There, you just have to book in our webpage. And your left, you will see Paranal. Paranal is the VLT, the Very Large Telescope. Paranal Observatory hosts the VLT, the Very Large Telescope, and the VLTI. The VLT is the most modern telescope in the world right now. Are 4 8.2 meter each. So there are 4 telescopes of 8.2 meter mirror diameter. And also we have the VST and Vista. The VST and Vista are mapping telescope or survey telescope that are also in Paranal Observatory. A little at your left in the bottom part says CTA Sur. It means Cherenkov Telescope Array South. This is a new project. It's going to be built in the future. They are 99 telescope, very special telescope. They are they will try to reach the gamma rays burst. The gamma ray burst, gamma ray will smash against that atmosphere, and then we will capture that collisions. Also, and the most important one is Armazones. Armazones is a mountain in front of Paranal, only 20 kilometers in front of Paranal, and then it's we are building the ELT. The ELT is the extremely large telescope. The extremely large telescope is 39.3 meters in diameter. Can you imagine? Today we have the ESO 3.6 meter. That was the first big one that we have in La Silla. Then we have 8-meter telescopes with the VLT, and now we are building a 39.3 meter in diameter with the ELT, the extremely large telescope. It's going to be ready in about around 2028, 2029, and it will be the biggest eye on Earth looking to the sky in the next decade. At your right, you can see Chagnantor. Chagnantor is a plateau in the Chilean altiplanic, about 5,050 meters above the sea level. Okay, ALMA is the Atacama Large Millimetric Array, the biggest radio telescope in the world. There are 66 antennas, and they also can do interferometry, and they can make one single virtual parabol or antenna of 16 meters when they can make this antenna bigger or smaller depending on how close the antennas are, the 66 antennas are. And you can see also in the bottom underneath the ALMA picture, you can see Apex. Apex is the Atacama Pathfinder Experiment. Atacama Pathfinder Experiment is just one antenna of 12 meters and was the first antenna that ESO located in the Chagnantor Plateau. So these are the telescope that ESO is operating in Chile or are going to operate in Chile. ALMA is another organization, and ESO is a partner in ALMA. So I think that we are ready to go to La Silla, but before that we have some questions. Even I can see we have a
we have a question. Usually,
yes.
About the ELT telescope. What is the latest status of ELT telescope?
Well, yesterday was in the surrounding of the ELT. We already finished 50% of the contraction, so we can say that we are plus over the 50% of the contraction time for the ELT. So I would say the status very well. It's going. They are building it. Nobody can get inside without special permission because they are it's under construction. So it's pretty well, and we hope to have ready the telescope for the first light. First light is when the telescope capture the first light of the stars for the year 2028 or so.
So we start then to go to La Silla, but first we start outside of Chile.
Yes, here we are. We're starting in Europe. Okay, you can see the countries. You can see the borderline of the country from in Europe that are part of ESO, and of course in 1960, in the 60s, these countries start to look up for a place around the world where to install this new big telescope. For those time, big telescope were 1 meter, 2 meter telescope. So they have to cross the Atlantics, and they look for a place, a site, a good site in Australia, also in Africa and Chile. And guess what? They found the Atacama Desert. in the northern part of this very skinny and long country. The Atacama Desert is the driest desert in the world, something that astronomers look for very specially, because a dry atmosphere, a dry desert means dry atmosphere, and with a dry atmosphere you have crystal clear sky, because there is no water in the atmosphere. That means that we don't have any too much turbulence in the atmosphere. So here we are arriving in the Atacama Desert, in the southern part of the Atacama Desert, where La Silla Observatory is. Here we are. This is La Silla Observatory, 156 kilometers north from La Serena city. I think we can do a flyover. Okay, here we are. This is a flyover La Silla. You can see that we have a couple domes there. You have the Danish 1.54 meter. Those are from the 60s, the 70s. Actually, are very new telescope. Most of the telescope today in La Silla are robotics. Okay, the 2.2 meter telescope today is just a Max Planck Institute telescope. We have the 1 meter Schmidt camera over there, and of course we also have the NTT, the New Technology Telescope. It's one of the telescopes that we are going to visit today, and the CEST, the Swedish ESO submillimetric telescope. It's a radio telescope, was the biggest radio telescope in the southern hemisphere before ALMA. And we have the Swiss 1.2 meter telescope and the visitor center. Of course, the 3.6, the biggest telescope that we have in La Silla is the 3.6 meter telescope. When we talk about 3.6, 2.2, 1.5 meter telescope, we're talking about the diameter of the main mirror. Okay, all these telescopes work with mirrors. So we have the main mirrors. We name them because the diameter of the main mirror. Actually, the 3.6 telescope means that the main mirror is 3.6 meter in diameter. Well, here we are in La Silla. First of all, let me give you a panoramic view of La Silla. It's amazing. You can see here the whole landscape. And by the way, we're looking to the sunset here. Well, in this same place, in the same point that I'm showing you today, July 2nd, 2019, we have 1,000 people. Why? Because we have the total solar eclipse of July 2nd, 2019. For the first time, the observatory has so many people in the mountain. You can see here also, here we have the radio telescope. Today, the radio telescope is out of order because all our efforts are in ALMA, the Atacama Large Millimetric Array that I showed you before, we talked to you before. And here you can see the mountains, which is amazing. The colors of the mountains, because the sunset and some cloud we have over there. Sometimes we have clouds, but in the night the wind take them out. And here we are. Well, first, I think the first thing we will do is to go inside of the telescope. But I would like to know, Felipe. Sorry.
Tell me, we have many greetings from Amsterdam, from Russia,
Yes.
from República Dominicana, Malaysia. We have different countries to see us today. Hello, everyone. Today is La Silla Virtual Tour Guide. So you can, if you want visit Chile, you can go to La Silla in the fourth region of Coquimbo region. You can visit La Silla Observatory. Go here and say, I'm here. I stay here in La Silla. So please leave your comments, greetings, any question you have about Euseus in the visit, telescope, astronomy, whatever you want. I invite you to leave the comments, please. So, what is the next point?
Well, our next point is the inside of the 3.6 telescope. You can see here how huge is the dome. This is an enormous dome. You can see the how big it is. Just take a look to this, I think, engineer that is working down there. Okay, let's say that this is 1.8 meter tall, and then you can see how big is the telescope and how big is the dome. This is a classical telescope, okay? It's what we call classical because it has this mount, the blue, dark blue part is a mount, is the mount where who is holding the telescope, and the mount is the coronal mount, okay? The coronal mount, and the light blue part is the telescope itself, okay? And it's classical because this is the way that we used to build telescope in those times, in the 70s. This this telescope was inaugurated in 1977, okay? So it's really huge dome. So how this work? Well, first of all, it's like in your house in the night. If you want to see the star, you have to open a window. Well, we open the window, and you can see the opening here, this window over there. Well, the picture is in daytime, of course, for to have the pictures, but in the day everything is always closed. Okay, you cannot open the telescope in the day. We do it in really seldom a special situation like this for to take this picture. Well, in the day we have to find in the night, excuse me, we have to open the window, and then we have to find the star or the object that we want to observe. So when we find that object, we have to point the telescope. Let's suppose that right now we're pointing to that object, and the light of the object of the star will go down, okay, and will go to the main mirror, okay. Remember that we were talking about mirrors. Well, the 3.6 mirror telescope in diameter is right here, okay. It's a mirror of about 3.6 meter in diameter. It has it's a curve, has a little curve, and it has a little layer, aluminum layer. Okay, so the light, because the aluminum is reflected to the secondary mirror. Okay, we have a secondary mirror inside here. Let me show you. It goes up to the secondary mirror, which is inside of this black tube. There is a second mirror, okay, smaller, and then the light will go back and will go through the center of the mirror down here, okay, and will reach this area where this cage is, okay. Inside of the cage, what we have is the instrument. Instrument is what we call a camera, a digital camera today, okay, here where the instrument are used to be installed. Okay, the instrument in this case today, I mean in the 3.6, we don't have the instrument here. We have the instrument in the third floor of this building. So what we have in the cage down here, we have the fiber optica, and the fiber optic lines will go to the instrument, taking the information from the telescope to the instrument. What the instrument does, well, the instrument in general can do two things. One is to make an image, of course, of the object that you're looking at, and also you can the instrument can analyze light, what we call a spectrograph. The spectrograph do a spectrography, analyzing the light that the instrument is getting from the star. And the light can give us a lot of information. In this case, we have a very special instrument. It's called HARP, okay? And HARP is a extrasolar planet hunter. Let's show you better this video that is running now. Why we call it, we call HARP an exoplanet hunter. Well, first, because we're discovering planets around other stars. Our solar system is not the unique solar system in the universe. Our solar system is one of them, and our solar system is very special. It has one star and have these 8 planets. Well, there is other solar system very similar, but how we can detect, how we can see this planet? Well, we cannot, because they're too far away, and the light of the star is too bright. So we cannot see the planet because the light of the star. So what we do is to detect the planet. How we detect the planet? Well, the planet will move, okay, will pull the star. See, like for example, our own moon pull a little bit our planet Earth, and we can see that's in the ocean. We can see that's the situation, and same thing happened with the planets around other stars. The planet will pull a little bit the star. So what you see here is of course is just a graphic, and but underneath in the video you can see the spectrum of the light, okay, and you can see how the spectrum of the light goes to the left and to the right, to the blue or to the red, okay. That means that what we really see is that the star is moving a little bit closer to us and farther from us. That means that if we detect that movement of the star, we know that there is a planet pulling the star, okay, which this pulling will pull a little farther away from us, that star, or will pull it a little bit closer to us. If you go to blue, will be closer to us, and if you go to the spectrum, go to the red, will go far away from us. Okay, it's very small pulling, so it's very difficult to detect. So the instrument have to be very accurate. Okay, and in this case, harps is a really accurate, high precision instrument. That's why we have found a lot of planets around other stars with harps, and actually around the world, in the astronomical world, internationally, we have found more than 5,000 planets around other stars. So that's the importance of the 3.6, because it has this instrument. Let's see if we have some comment or some greeting or question from anywhere in the world. Felipe?
Sharon say that the dome is huge. I visit 3.9 meter in Australian telescope in Sydney Spring Observatory in Australia. I can imagine the difficulties in doing maintenance on the telescope. The maintenance.
Yes, it is.
Oh,
Well, I have a story about it. See, the dome that I'm showing you right now here, that comment remind me this. The dome is, as you see, the telescope is from 1977. So the dome moves over wheels. Okay? Has these motors and the engines that move the dome with and the dome is over wheels. Well, the wheels, nobody make them anymore, so we cannot go to the industry and say, hey, I need 2 more wheels, please, like for your car. No way. So what's happened is that now whenever we need a wheel, we have to make it ourselves. Okay, so it's kind of hard to maintain, but the electronic people, engineers, and engineer in general, and all the maintenance people doing great job in La Silla to keeping this old friend of us working for so many years.
and apart, we have a more greetings to Australia, Munich, and Italia. Hello
Oh,
to Italia, and
benvenuto.
we have a lot of people see us today.
Great.
For
Well,
from new people see us in this point, you can leave your questions about astronomy, about the telescope you see in the virtual visit. So leave your comments, greetings, everyone you want to know about astronomy or ESO. So this is an old telescope, right? So what is the form of the new telescope?
before we leave the telescope, I would like to show them very short video of how the telescope work at night. Let's do that, please, Felipe.
Let me show you.
Well, there you go. This we could look at the video how the telescope works, and well, we will not go to the time pass running very quickly. We will go to our next telescope, just to keep in mind and keep in your eyes this image, because this is the old way to make telescope. Okay, we don't make telescope this way anymore. As I told you, the dome and the mount, the blue part, as I told you, is the equatorial mount. We will go to what we call the entity or the new technology telescope. Okay, here we are. Here, this is the new technology telescope, and you can see this is a square telescope. Okay, while this is a round telescope. Okay, classical dome. Okay, so just making sure that you can see the difference between both of them, and we will see what is new about the new technology telescope. Okay, let me go inside of the new technology telescope. Well, this telescope is from the 90s. Okay, first of all that we can see is that quote is much smaller than the 3.6. But not so, because the mirror, as I told you, the mirror is the main part of a telescope. Well, in this case, this mirror is 3.58 meter in diameter. The other one, the one that we just visit, is a 3.6. So it's almost the same in diameter, I mean. Okay, but the main difference and the first difference is the mirror, because of what we made the mirror. Okay. The 3.6 meter classical telescope, we used to use a ceramic, okay, an old ceramic that do not allow us to make mirror bigger than 8 meters, okay. But with this one, with the new ceramic, it's called Cerodur, we are allowed to make mirrors of 8 meters in diameter. Like in Paranal, for example, the VLT are 8.2 meter in diameter telescopes. So this mirror is the first mirror that we made with Cerodur. Cerodur is a very special ceramic which allowed us to make bigger mirror in diameter, I mean, but also not so thick, very thin mirror. In this case, you can see a mirror of 28 centimeters thick and 3.58 meter in diameter. The VLT, for example, the very large telescope unit, the mirror is 8.2 meter in diameter and only 70 centimeter thick. That means that they're very thinner, very thin mirrors. Okay, what that means, that we can make a smaller mount, a telescope or buildings. In this case, for example, the mounts also allowed us to make a mount, not a quadral mount, but an alt azimuth mount. That means that the telescope moves in 360 degrees. Actually, in this case, this whole building moves in 360 degrees. When you're observing, you're pointing the telescope, and then what's happened is that the whole building is moving around like a carousel, like we're trying to do that movement here with this 360 degrees virtual tour. And that means also that the whole building is a smaller building than the other one. That helps a lot. And the other thing that we find out with this new technology telescope is that actually we don't need to build the telescope very high. Let me show you if you could understand what I'm talking about. See this the 3.6. We were there just a couple of minutes ago. The 3.6 is silo of 50 meters tall, and the first 25 meters. It's not the telescope. The telescope is about 25 meters above the ground. Okay, in those times we suppose that was a better way to do telescope, to build telescope, because we thought that as higher you put the telescope was better, because remember that the ground will absorb heat during the day. Okay, and that heat will go out in the night, will become cold, and the heat will go out and will produce turbulence around the dome. That's why we thought, oh, let's put the telescope very high, 25 meters, so we avoid those heat that will produce turbulence. Okay, but we find out that it's better to build telescope like this, ground level, and then make a different type of a structure or dome or enclosure, we call it today. So that's why we open the whole ceiling of the building all the way down. Okay, so that allows the wind in the night. When we open in the night, the wind will go through the whole building and will cool down the inside. Actually, today we cool down the dome during the day. The dome have to be closed, and to avoid that we accumulate warmness inside of the dome, what we do is to cool down. We have cooling system, so we keep inside of the dome during the day. We keep the same temperature of the night before. In that way, when we open in the night the building, we will have the same temperature, and we won't create artificial turbulence around the dome. That's pretty good, and works very well. So as you see, our main thing here for the astronomers to not produce turbulence, do not have turbulence in the atmosphere. Why is that? Because the light that we are trying to capture is light from some time, for a start, that are very far away, 10,000 years away. So the light will travel so many years in the empty space, but when the beam of light reach the atmosphere, what will happen is that will get disturbed. The atmosphere will make a distortion to the light if we have too much turbulence in the atmosphere. In that way, the beam of light will go straight away to the main mirror, and the main mirror will reflect the light as we get to know in the other telescope. We'll go to the main mirror. The main mirror also is a little curved, has an aluminum layer, will reflect the light to the secondary mirror. Up here, you can see a little bit the mirror right there, the secondary mirror. And in this case, the light will go down, down, down to the center here. And here, we cannot see this dark part, black part that you can see. There is another mirror, a third mirror in this case, and that third mirror is flat and will send the light to the right, or it will send the light to the left. In that case, we will have the instrument not underneath the mirror, but at the sides of the mirror, what we call Nasmyth instrument. That's the door where you cross the door and you will be inside of the room where the instrument is. Remember that the instrument is a camera, it's a digital camera. It's a very special digital camera, and the camera will do the image or will analyze the light that we are receiving, okay? Also, and even important, is the mirror, as I told you, with this new technology, with this new Cerodur ceramic, will make the mirror very thin. That means that the mirror is flexible, okay? During the night, when we are observing, the mirror could lose the curve that it has, okay? So to avoid that and to have always a perfect surface of the mirror, we use what we call active optic. Active optics means that underneath the mirror, maybe you can see it there, there is some actuator. This actuator, they push the mirror, okay, up in order to keep always the surface perfect of the mirror surface perfect. So that's called active optic. So that's why we have the NTT, the new technology telescope, and actually the telescope that you're looking at is a prototype telescope for the VLT, and of course today for the ELT. All the basic technology, the basic new technology, the dome, the structure of the building, the mirror itself, and everything else were proved in this first mirror, in this prototype telescope, which is working very fine until today. Actually, I think now we can go to see how the astronomer used the telescope in the night. I think we have a video working for the astronomer working in the control room. There we go. Maybe you can explain us what's going on here, Felipe.
We have the control room of La Silla in particular. So we have two sides. The left side is the part of NTT telescope, the latest last telescope CEST, and the right part is a 3.6 control room, but have the same persons. And in the video we see a speed video. So we have two kinds of people. The first one is in the dark clothes is the operator of the telescope. That person move the telescope, see the space, and prepare the telescope in today for the astronomers. Who is the astronomer? The astronomer is in a color cloth. So the astronomer prepare 1 year in 1 years prepare the proposal of observation. So send to Germany to the ESO in Germany in HQ, see the proposed different proposal for one night, and give observation time to astronomer. So the astronomer come to La Silla and work together the controller. So this is how work in a control room. All night, the control room work with the telescope. The operators work every week preparing the telescope for one observation, and the next night prepare the telescope for the other observation. So we have a lots of work today in a day and in a night. In a day, prepare the mountain saying the prepare the instruments for observation, and in the night the astronomer come sit in one part and put the PC and controller in the other part sit and make start to move, open the gate, the dome, and see the sky all night around 8 p.m. to 8 a.m. In a summertime. So this is how work, and this is part of the magic of the astronomy born. So we have a top 10 video about the principal discovery, right?
Yes, please, let's take a look to the main discovery of ESO telescope in Chile.
So we go.
Observations with ESO telescopes have led to many breakthroughs in astronomy, and over the years have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago. a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
All right, there we have the top 10 discovery of the ESO telescope. There is a couple questions that I would like to answer. One is how are the telescope powered so far out in the desert? Solar? Yes, it's solar.
That's right.
We have a solar plant here in La Silla, and it powered the whole observatory. Even we have we do more. We make more power than we need, so the extra power we put it back in the main current line of Chile. Secondly, there is another question. So does it mean there's not much difference between putting the main telescope mirror near to the ground as compared to placing it higher up? Yeah, well, the thing is that in the old time, as I told you, the 3.6, let's see if we can go to that. Let me try to show you I will show you. Here we have the 3.6. As you can see, the 3.6 is a huge building, okay? Means that all this part of the building, all the building in the 70s, in 77, when the building was built, was inaugurated, all this first from the ground to 25 meter was with office, okay, people working, and also computers. okay, and the telescope was 25 meters above the ground. So what's happening here in first, that why they did that, because they thought that the ground in the day will absorb that warmth, the heat, and the heat will be released in the night, so that will produce around the dome this disturbance. But what's happened is that the humans and the computer also produce heat, and that heat went up to the dome where the telescope is, and start to producing bubble heat inside of the dome. So that's why they decide to take everything from the bottom part of the building, and now the building is empty, completely 100% empty. Okay, to avoid that humans and computers produce this heat. Okay, so then they find out that maybe it was a good idea to build this kind of telescope. Here's the MTT. See, it's a square one. We open in the middle. It's a ground level, because we are ground levels, but we can open the whole. Actually, we almost open the whole building in order to equalize the temperature inside and outside. And also, of course, during the day, while the telescope is closed, the dome is closed, we cool down the dome. So when we open the dome in the night, there's not different temperature inside and outside, so we don't produce this turbulence. Okay. Hopefully, I answered the question that you got. Well, we have just a couple minutes more, like 12 minutes, and I could not stop not showing you this picture here. You can see, I think many people that is watching us right now is from the northern hemisphere, and here I'm showing you the southern hemisphere, the southern sky. Okay, actually, for those that live in the northern hemisphere, maybe you recognize this. This is one of the constellation very well known in the northern hemisphere, Orion constellation. Of course, because we are in the southern hemisphere, we see the constellation upside down. Okay, the head of the hunter, the Orion is a hunter, is upside down, but we can see here the Orion belt. Okay, here the three star that we call it the Orion belt right away. Well, actually, in Latin America, we call it the Three Marias, las Tres Marias. And this is the Orion belt. And here is very nice to see in this picture. Remember, this is a camera. It's a digital camera picture of the sky. Here we can see the nebula, the Orion Nebula. Here is a cloud of gas and dust where thousands of stars are burning. Okay, so this is one of the constellation, the northern constellation. Also up here we have another northern constellation. This is the big dog. Here's Sirius, the brightest star in the night. And then we have one leg of the dog, another leg, the back part of the dog, and here we have the big dog. Well, but you know that if you're from the northern hemisphere, you know this constellation. What I want to do now is to show you the southern constellation of the southern sky. See, this is the Milky Way. We're following the Milky Way, and we go right down to the center of the Milky Way. Is showing up here. Is right here, in behind the 3.6. Actually, we can see here the Scorpio constellation, okay, and the tail of the Scorpio is close to the Milky Way center, okay, and this is the Milky Way. All right, so this is the sky that Magallanes, you remember Magallanes, who was the first navigator who went around the world 500 years ago or so, and he found the first thing that he saw in the skies when he crossed the Ecuador was the Magallanes cloud. Here we have the two Magallanes cloud. Well, we call it Magallanes in honor to Magallanes, of course, and he thought that these were clouds. That's why we call clouds atmospheric cloud, but they're not atmospheric cloud. They are galaxies. They're two satellite galaxies to our galaxy. Actually, they are going around our own galaxy, okay? And one very important thing that Magallanes find out was that he can use these two clouds in order to find his way navigating in the southern seas, okay? Because in the southern hemisphere, we don't have the North Polar Star as you guys have in the northern hemisphere. In the northern hemisphere, you just look up to the north and you will see your northern star, and you can follow that star, and you always know that you're driving or you're walking or wherever or navigating to the north. In the southern hemisphere, you don't have that. We don't have any star in the southern celestial pole. Okay, what is the southern celestial pole? Is the center of where all the stars are going around. Let's see what Magallanes did. Well, he took the main Magallanes cloud, the one is in the top, and he took the small one, and he make a triangle, an equilateral triangle, an equal triangle, and then here he found out that was the center, the celestial pole, the southern celestial pole. But also, if you come to Chile or you come to the southern sky, you will find this very well-known constellation is the southern sky. Here you have it. Let me show you closer to you. Here's the southern sky, very well known also in the southern skies, and you can also use it to find the southern celestial pole. How you do that? Well, you take the long stick. This is the cross. Okay, you have the long stick, and you take that stick and you make it virtually 3 times bigger, 3.5 times bigger. 1, 2, 3.5, and then you are in the same point where the Magallanes cloud are pointing, right here. So there is your southern celestial pole. That means that if you make a line to the ground, you will find the south. See, actually, we're northern from La Serena, and here's some light from the La Serena city. Okay, and also one more thing that I want to let you know is that we also have our own history about the sky, because the pre-Columbian people, okay, people that used to live in Chile and in Latin America before the Spanish came, they were very good astronomers too, but they have different constellation. For example, they have this nice constellation because the Milky Way was so bright that dark spot in the Milky Way were so dark that they start to see some things in this dark spot. For example, let's see if you find out. Here we have the Llama constellation. Here's the head of the llama, and then we have the body of the llama right here. Okay, one leg, another leg, the neck, and the head, and here's the eye of the llama. This is what we call the Llama constellation. What are these dark spots? Well, these are cloud of gas and dust, very dark, very dense, that doesn't let any light to come in through it. That's why we see it dark, and they saw it very well. They didn't have any light pollution, so they call this the Llama constellation. Of course, they also have the Bear constellation. This is the Bear constellation. We used to call the Coolsack. The Western people call it the Coolsack. We call it the Bird. And we also have the Snake constellation, and so on. All these animals were coming down to this river because for them, the Milky Way was a river, okay, where all these animals came down to take water. All right. Well, I'm so sad that we have to say goodbye because
we have just time.
Yes, Felipe?
We have out of time.
Okay. Let's walk
to the hotel.
To the hotel right away. Here we are. I don't know if there is any question before we leave. We will invite you a coffee if we have a couple minutes to have a coffee. We will walk in the night through the telescopes to the canteen or to our cafeteria where we can take a coffee, and also invite you. Okay, I don't know if there is any question that we can answer, Felipe. Or
we have a last question.
All right.
Will we get a tour of the ELT when it is almost done with construction?
Well,
I hope.
Yes, we will, but not when it is almost done, when it's done. Okay, that means that we have to wait for the full completion completion of the contraction, and then I'm sure that we will have tours also. So we have to wait, I guess, until the year 2030. So, but hope that we will be there waiting for you to visit us. But remember that La Silla Observatory, Paranal Observatory are open for you to come every Saturday at 10 o'clock in the morning or at 2 p.m. in the afternoon. You just have to go to the ESO.org webpage, and you will find out the link that will take you to our booking system. You just have to book in advance. We have places there every Saturday, and we will be happy to have you with us every Saturday in the morning or in the afternoon. So also remind you that all these picture videos that we show you, they are in our webpage, and thousands of pictures and videos, and in different qualities, so you can download them from free. Also, we have news every week, news about the latest discoveries of ESO telescope in Chile. So please visit us and come back to this, to our to this same virtual tour. We have virtual tour of La Silla and Paranal every Saturday at 11 a.m. Chilean time, and they are in English and Spanish. So we have the same virtual tour for La Silla and Paranal in English and Spanish. So we thank you very, very much for you to be with us today, and thank you for your comments, your questions, your greetings. We're so happy to have many people from all around the world with us today, and we will see you next week again. Okay, so I would like, I don't know if there is another question or greetings from all of you. I understand that people from all over the world. Thank you very much.
So thank you for leaving the comments. Remember, search the ESO.org to see the latest news wherever you want about the ESO, the telescopes of ESO, and astronomy. Actually, astronomy. So
Yes.
see you the next week, and goodbye.
Yes, and follow us in our social media in Facebook Astronomy, ESO Astronomy, and also in YouTube, of course. Follow us in Facebook. You can put any question, you can ask any question, and we have a team of people who will answer the question about astronomy and about the organization. Thank you very much, and see you next Saturday.